Alright, let's get our hands dirty. In any big industrial plant, you've got a universe of pipes. They're the arteries and veins of the whole operation. Fluid, whether it's water, oil, or some exotic chemical soup, is always on the move. But here's the thing. It's not a smooth ride. Every time that fluid hits a corner, split joint, things get messy. It tumbles, it swirls, it loses energy. We call these energy losses head loss, the nemesis of efficient plant design. If you don't account for them, your pumps will be undersized, your system will underperform, you'll be chasing problems you can't see. So what's our mission today? We're going to demystify this chaos. We're building a laboratory experiment, a playground for fluid dynamics, to see exactly what happens inside common pipe fittings. We're talking elbows, T's, Y's. The idea is to stop guessing and start measuring. We want to see the flow, measure the pressure drop, pin a number on how much energy each fitting steals from the system. Every good experiment starts with a good setup. Ours is a closed-loop test rig. Think of it as a racetrack for water. We use a pump to get the water moving. This isn't just any pump. It has an adjustable speed control. This is critical because it lets us test the fittings at different flow rates, which means we can explore a range of Reynolds numbers. The water is at room temperature, which keeps things simple and safe. To know how fast our water is going, we need a reliable flow meter, a magnetic flow meter, an ultrasonic flow meter. They're non-invasive and super accurate. The heart of our rig is the test section. This is where the magic happens. We've designed it so we can easily swap out different fittings. Marketing. Close-up of the interchangeable test section showing a 90-degree elbow installed with pressure tap hoses connected. We need long, straight runs of pipe before and after this section. Rule of thumb, at least 10 pipe diameters upstream and 20 diameters downstream. This gives the turbulent flow a chance to settle down and become uniform before it hits our test fitting. It also gives it space to recover afterward. This ensures we're measuring the effect of the fitting itself, not leftover chaos from some other part of the pipe system. To measure the pressure drop, we use pressure taps. Tiny, carefully drilled holes in the pipe wall, one upstream, one downstream. We connect these taps to a differential pressure transducer. This amazing device measures the tiny difference in pressure between the 2 points with incredible precision. Choosing the right transducer is key. You need one sensitive enough to pick up the small losses from a gentle bend, but robust enough to handle the big drop from a sharp T-junction. Now, let's introduce the stars of our show, the fittings themselves. We're not just testing one or two. We've got a whole lineup, each with its own personality and its own special way of messing with the flow. First up, the classic 90-degree short radius elbow. Standard sharp corner, a real troublemaker, lots of turbulence, and a big pressure drop. It forces an abrupt, unnatural turn, chaos for flow. Expect serious flow separation here. Next, the gentler 90-degree long radius elbow, much more gradual curve. Water has more time and space to turn. Result, smoother flow, less separation, and lower energy loss. We'll also test a 45-degree elbow, even less disruptive. For the ultimate gentle turn, a large radius bend, radius 3x diameter, likely the champion of low-loss direction changes. Then, junctions, where one flow becomes two. Start with a symmetric Y joint. Pipe splits into two equal branches at a gentle angle. Flow should divide fairly evenly. But there's a stagnation point at the apex. Watch for effects. Contrast with a T-joint. Branch at a hard 90 degrees. A violent divide. Expect huge turbulence and recirculation zones and very large pressure loss for the turning fluid. Finally, other cases. A 1/3 branch, asymmetric junction. How does the fluid choose its path? A sudden expansion. Diameter abruptly increases.
Here's the step-by-step plan. Precision and repeatability are the names of the game. First, we install our first fitting, the 90-degree short radius elbow, into the test section. We check every connection to make sure it's tight and leak-free. We fully bleed the system of any air bubbles. Safety first, always. Guards are on the pump. We know where the emergency shutoff is. With everything set up, we turn on the pump. We set it to our first target flow rate. The flow meter gives us a live reading of the volume passing through per second. Q. We let the system run for a few minutes to stabilize. Once steady, we record the flow rate. Our differential pressure transducer measures the pressure drop, dP, between upstream and downstream taps. We record dP, we note the water temperature. We don't just take one measurement. We repeat this across a whole range of flow rates. Maybe we'll test at 10 gallons per minute, 15 gallons per minute, 20 gallons per minute, 25 gallons per minute. This gives us a rich data set and lets us see changes as flow gets faster and more turbulent. We plot results against Reynolds number. Once we have a full set for the first fitting, we shut down the system. We drain the test section. We swap in the next contender. Then we repeat the entire process. Yes, it's meticulous. Yes, it's repetitive. Data is just a pile of numbers until you give it meaning. Our first step in data reduction is to take the raw measurements and convert them into standard engineering units. We have the flow rate Q in gallons per minute, so we'll convert that to cubic meters per second. From Q and the known cross-sectional area of our pipe A, we can calculate the average velocity V of the water. V more Q A. This velocity is the V in our all-important head loss equation. Next, we tackle the pressure drop dP. Our transducer gives us a reading, probably in pascals or psi. We need to convert this into head loss, which is an equivalent height of water. The formula is HF, or Nash, dP, d, Rg. R is the density of the water, and G is the acceleration due to gravity. This gives us our head loss in meters. This value, AF, represents the amount of energy the fluid lost, per unit weight, as it navigated the twists and turns of our fitting. It's a direct measure of the fitting's inefficiency. Now for the grand finale, calculating the loss coefficient, K. The K factor is a dimensionless number that neatly packages up all the complex physics of the fitting's geometry into a single, useful value. The definition is K, HF, V squared over 2G. That's the velocity head, V squared over 2G. For the 90-degree short radius elbow, it's going to be brutal. As the water tries to make that sharp turn, it can't hug the inner corner. It separates, creating a low-pressure zone with a swirling, recirculating vortex. The flow slams into the outer wall, creating a high-pressure zone. This chaos generates intense turbulence, the reason for the high K factor. Downstream, the velocity profile is completely skewed with the fastest-moving water stuck to the outer wall. In contrast, the long radius elbow will be much more civilized. The large radius bend will also be much more civilized. The gradual curve helps the fluid stay attached to the walls. There will still be secondary flow, a corkscrew-like motion. These are Dean vortices, but far less intense. Flow separation will be minimal or non-existent. Pressure drop and K factor will be a fraction of the sharp elbow. That's the hydrodynamic argument for sweeping curves over sharp corners. The T-joint is fascinating, especially when diverting flow into the branch. The straight-through flow is disturbed. The flow turning into the branch sees extreme separation and loss. So, we've run the test crunched, the numbers seen the flow. What's the final takeaway? Our experiment confirms what the textbooks say. With real, tangible numbers we generated ourselves. Sharp fittings are energy hogs. 90-degree short radius elbow branching flow in a T-joint. They create massive turbulence and flow separation, which means wasted pump energy. The verdict is clear. Avoid them when possible. On the flip side, gradual changes are your best friend. Long radius elbows. Large radius bends. Low K factors mean they steal very little energy from the flow. Same goes for expansions. Smooth blended transitions versus abrupt, sudden transitions. For a plant engineer, this is actionable intelligence.
When designing a new system, use sweeping bends instead of standard elbows. This leads to real energy savings over the plant life. We calculate a K factor for every single data point we took. With our calculations complete, we move to visualization. We're going to make some plots. The most important one will be a graph of the K factor versus the Reynolds number. For turbulent flow, we expect the K factor to be fairly constant, but this plot will prove it. We'll plot the data for all our different fittings on the same graph. We'll immediately see which fitting has the highest K factor, the short radius elbow, and which has the lowest, the large radius bend. This is the story our data tells, but numbers are only half the story. To truly understand what's happening, you have to see it. That's where flow visualization comes in. We can inject a little bit of dye into the water just before the fitting and watch how it twists and turns. For a more high-tech view, we can use particle image velocimetry, PIV. Seed the water with tiny reflective particles. Illuminate them with a laser sheet. A high-speed camera captures the particle movement. Software turns it into a detailed map of the velocity field. This is how we can literally see the invisible chaos of turbulence. Sudden expansion is all about flow separation. Entering the larger pipe, the flow can't instantly fill the area and forms a jet. The jet continues briefly, then violently expands. Large, stable corner vortices form and just churn, sucking energy from the main flow. A smooth, blended expansion acts like a megaphone, expanding the flow gradually. That prevents large-scale separation and lets pressure recover. The result is a much, much lower K factor. Manufacturing and installation matter. Smoothness of a weld. Slight misalignment of a flange. Burrs inside a threaded joint. All add small-scale turbulence and extra losses. For critical systems, test the actual fittings you plan to use. This experiment is the blueprint empowering engineers to move from estimates to evidence. Where do we go from here? The possibilities are endless. Test two elbows close together. Investigate an upstream valve's effect on a bend. Use PIV to map turbulence in greater detail. This isn't the end, it's the beginning. It gives engineers a powerful tool, a hands-on methodology to understand hydrodynamics. By busting myths and measuring reality, we build smarter, more efficient, and more robust systems. And that right there is a story worth telling.